Hi, I'm Don Cohen from Michigan Metrology. I help people solve problems related to squeaks, leaks, friction, wear, appearance, adhesion, other things that relate to surface roughness. I'm here today to talk about an application. These are clutch plates that we're measuring. This is what's in a transmission, allows you to change gears. So this plate engages against a friction material. And so the friction of this surface against that mating surface is what allows this clutch to engage. And the challenge we have with these types of parts is there's this right amount of friction that we strive for. We get that by choosing the materials properly, the surface roughness property, and then the lubricant additives. On the other end of that, the problem is if the surface texture isn't quite right, we can cause premature wear of the friction material that this is mating against, and that's another problem. And also, if the friction isn't right, we may induce some vibration causing noise. A little bit of the background. I work with Bruker Corporation as a value-added partner here in Detroit, and I have this wonderful machine called an NP Flex optical profiler that measures surfaces in 3D. So we're able to look at surface texture in great detail. We're able to put large parts underneath and heavy parts on there. And we also have this long working distance objective lens, which allows us to be fairly far away from the sample. This is basically a microscope. One lens is imaging the surface. The other lens is working as what we call an interferometer. It's the interferometer that gives us the height on the surface, and the standard microscope objective gives us the image. On the screen here, we're seeing the image that the microscope sees. So these are shot peen surfaces. There's a little indentation. As I bring the microscope down closer into focus, you see these twinkly patterns, which are the interference fringes that are occurring when the surface is in absolute best focus. These features that have that little stripe pattern are in best focus. And as I move down closer to the surface, I can see these fringes fall into the valleys on the surface. So basically here I'm on the ridges that surround the little indentations, and then the little peening marks are here. And so what this machine is going to do is it's going to scan from the top down, looking at each point in the image, and basically figuring out when it comes into focus. And it can localize that focus to within nanometers. The microscope slightly moves up, now it's coming down, and then that interference fringe pattern will sweep across the surface. And once it's done sweeping across the surface, it pops out a color contour plot of the surface. So the red areas are high spots, and the blue areas are the deep valley structures that are made by that shot peening mark. And what we're able to do is move cursors around and look at the profiles along the X and along the Y direction. So we can look at the 3D nature of the surface. We can put a lot of information on one screen. Just a good visualization of that 3D texture can sometimes help you figure out what's going on. In this particular surface, there's some interesting things to talk about. One is we can just have the basic 3D roughness parameters like SA and so forth. We also, though, can analyze the surface much the same way a stylus will analyze it. We can move around with these cursors and look at a profile and then show for that profile the same analysis that you'd get for a stylus profilometer. What distinguishes between PA, RA, and WA is filtering. And if you go to our website, there's all kinds of discussions about the filtering to get into a big deep dive on all that. Another thing that's useful is an analysis called bearing ratio. In a clutch plate, we're talking about two surfaces coming together. And so what we're concerned about is, okay, as it makes contact, how high are the peaks that we're interacting with? And then once we kind of make contact, how much valleys remain? And so the graph here is basically showing at the highest point, we're making no contact with the surface. And as we move through the surface, we're making more and more contact. And so the shape of this bearing curve is a nice indicator as to what the nature is of the texture. We derive some parameters from the bearing ratio curve. So as one machines a surface or processes it, we can tune the peak heights versus the valley depths independently in order to optimize that surface. And so whereas the average roughness may be pretty consistent, I can understand that by looking at the bearing ratio curve. This actual part was in production for a number of years. Millions and millions of those are being produced. And they were being controlled, not by a 3D optical profiler, but once we do the research with the 3D optical profiler, many times we can get by with a basic 2D profiler in production. As I mentioned, I'm here to help people solve problems related to friction and wear and surface finish. Feel free anytime to visit the website. We have a lot of blog posts, animations, and glossaries. Also on the website is the ability to set up a meeting via Teams, and we can meet and discuss your applications. If you're in the Detroit area, feel free to set up a time to come by and visit, bring some parts. And again, just feel free to send a few samples in for no charge. I'll take a quick look and see what we can do.